So let's talk about buffers as our first bit of notes. Have you guys ever heard the term buffer in like common context maybe? What way? Like a buffer zone? Yeah. You might have also heard it's like, oh, can you tag along with me to this party? I need someone who'd be a buffer between me and my ex. Maybe? Like a block. Yeah, like a block kind of thing. So, just thought it would be funny to give you guys a common language for it. All right. But when we're talking about buffers in science, we are talking about a solution. It's a solution with an acid and its conjugate base. Or it could be the other way around. It could be a base with its conjugate acid. And it's really important that you have both of those components there because that's going to help it maintain the pH. So basically what that means is that if I have a solution that is a buffer, I can add some acid to it and the pH won't change. I can add some base to it and the pH won't change that much. So I'll switch back just quickly to the PowerPoint because I had a good image in there just to see what buffers do. Don't worry, this will come back. But you see here how we have water and we have water with a buffer. If I add an acid to just plain water, it's going to lower the pH quite a bit. But if I have a buffer in my water, it's going to help prevent that change. So in this case, it's changed, but like not as dramatically. So the buffer acts in there to help neutralize anything that's being added to it. It can also work in reverse. This is the amazing thing about buffers. It's both directions. So I have water and I add base to it, it's going to raise the pH. But if I have a buffer in there and I add base, it's going to like change it maybe slightly, but nothing dramatically. So buffers are there to help maintain pH. Really useful. And in fact, we have buffers in multiple situations. We have buffers in our body because our body, it's really important for us to maintain our pH. I think we're at 7.4 is what our body operates at. You also use it a lot in industry because you don't want degradation of chemicals and things like that, or maybe certain reactions prefer certain pHs or material and things like that. So buffers are really, really important. The thing you have to remember is that buffers have different capacities. So some can take quite a bit of acid and quite a bit of base, some can't. So that's something we have to remember. Different buffers have different capacity. And when I say capacity, it's just like when you think about capacity in a sense of, does this room have capacity? How much it can take before the pH changes by 1. We could also look at it as limitations. So basically, AKA, how much can it take before its pH changes by 1? So that's usually what we use as our definition. So are we okay with that so far? I'm trying to move my wires around. So buffers, really, really useful. And the good news is that the ocean has a buffer as well. So with ocean acidification, yes, it's happening, and yes, that's bad news. But the good news is we have something in place to help us maintain that buffer. So in the ocean acidification essay that equation we looked at yesterday, can I move it? All right. Do you remember this part of the equation here? So the buffer component in this equation, I'm just trying to grab a marker that I haven't used yet, is the bicarbonate and the carbonate. So the bicarbonate is our acid, and the carbonate is the conjugate base. So our ocean has carbonate and bicarbonate in there. That is acting as our buffer, and that's going to help us maintain that pH. So if, for example, I add base to my ocean, it promotes the forward reaction. It's going to the bicarbonate is going to neutralize it by donating a hydrogen ion. If I add acid to my ocean, then those hydrogen ions are going to be accepted by the carbonate and move it backwards to mop it up and maintain that pH. So really great system, really important for the ocean to do that, because there's obviously a lot of living creatures in there that depend on that pH to be at a reasonable amount, so that way they can survive. And you also have to remember, evolutionary wise, they have evolved for this certain pH. So that's the pH what we're looking at, or sorry, that's the buffer system we're looking at in the ocean. Now, this buffer system has worked really, really well for about 750, 100 years. I'm just gonna write down the number because I'm not good with numbers. 750K, that's the word I was looking for. So for 750K years, we are looking at keeping that pH around 8.2. So for a very long time, that's what the pH of the ocean has been. So it's worked really, really well for us. Now, there's several problems and several things to think about when we are considering buffers and when we're thinking about climate change and how climate change affects what's going on. One of the important things to remember about buffers is that when they become diluted, the pH doesn't change, but their capacity to take on more acids and bases decrease. So I'll write that down. I'll put a little star next to it. So when buffers are diluted, the pH doesn't change, but the capacity is reduced. And that means basically it's a weaker buffer. And so it's less resistant to change. Does that make sense? So if something that might have been able to handle, say, for example, like 100 mils of 2 molar acid now can only manage 50 mils of that 2 molar acid. Does that make sense when I say reduced capacity? What you then need to think about for this essay is our ocean buffer getting diluted? So think about climate change, think about the melting ice caps, think about what those melting ice caps are doing to the concentration and salinity of the water, and how is that going to affect our buffer system. So there's multiple layers to this essay. One of the layers you're going to be talking about is buffer, and one of those components of the buffer you're going to be talking about is the dilution of the oceans and how that's bad. It's not good. All right, I think that's, what else did I want to do before I did the video? Carbon cycle. Okay, cool. Let me pass out those notes because I wanted to print out some images to help you see carbon cycle. When you guys research this essay, it's going to make you depressed. FYI. And to be sad. Well, because like the world's all doom and gloom, and you're like, I can't afford a house. Climate change is bad. There's all political injustices, and now I'm just going to add another one to that plate of worry that you guys have, that I have too. Yeah, it's ocean acidification. So, because of the boomers, there's the boomers, us millennials, and you, what are you guys, Gen Z? Yeah, Zoomers? We're gonna have to fix this problem ASAP! Yeah? No pressure, and also while you're doing that, you won't be able to be paid a living wage, and you can't buy a house. Just really jabbing the knife in there, making you real depressed. I'm sorry. I cope with my worries using dark humor. Because if you don't laugh, you're just going to cry. All right. So, I'll talk kind of quickly through this because I don't want to go through it in huge detail. I just want to point out some things to you guys and how you're going to relate it into carbon cycle. So have you guys ever seen the carbon cycle before? No, that's yes, no, some yes, some no. That's okay. Yeah, so carbon cycle is just talking about how carbon gets cycled throughout an environment. Because remember, matter can't be created or destroyed, and when we die, we're just decomposed, and then all our atoms are recycled to make something else. So carbon obviously is something that's really essential to get cycled through because we need carbon as a building block to life. So carbon can be found in all four spheres of Earth. Do you guys know what spheres we're thinking about? Yeah, the different hemispheres and things like that. So you have the atmosphere, which is the air. And so what's carbon when it's in the air? Carbon dioxide. There is the biosphere, which is every living thing. So carbon's in the living things itself because we're building blocks. There's carbon in the geosphere. So geosphere is talking about land and things like that, rocks. And we get carbon in rocks, like in limestone, calcium carbonate, for example. And then you also get it as like oil and coal as well, carbon. And that's in the geosphere. And then the last one is the hydrosphere, which is water. And carbon gets cycled through there with the ocean acidification becoming carbonic acid. So we have carbon throughout these geospheres and they're getting cycled through. So I have two images for you guys because I couldn't find one that I liked better because this one I like because it shows the ocean acidification in here and it shows the link to the biomass and things like that. But this one here has equations, and so I've given you both. So the thing to remember about the carbon cycle is that this was a really delicate balance for a very long time. Carbon was being cycled through our four different spheres. The main way that carbon, let me backtrack. Most of the carbon was locked away as in the geosphere in forms like oil, fuel, coal, that sort of thing. Yeah? Like, you good? So before the Industrial Revolution, if carbon was getting into the atmosphere, it was getting in through volcanic eruptions and things like that, and from living things breathing out carbon dioxide. So it wasn't that much that was in the atmosphere. And then that got dissolved into the oceans and had that certain pH, and then living things obviously die and get compressed, and that then goes down here. It can become rocks again, and then the cycle keeps going. So that's what happened for a very long time, and it was all fine. Then the Industrial Revolution happened, and we started burning things. With that burning of the fossil fuels, we are now have released all this carbon dioxide and the greenhouse gases into the atmosphere. So we've disrupted that balance. We've taken something that was solid, locked away, now putting it into the air, and now that it's a gas, it's starting to dissolve into water and things like that. And so this is where the increase in the carbon dioxide concentration is coming from. So if you look back at this equation, remember how I said that this carbon dioxide, that increases in concentration because we have more carbon dioxide from the burning of the fossil fuels. It shifts that reaction going forward, and now we're getting the ocean acidification process. Are we okay with that so far? Cool. Sad stuff. So this is the flip side of climate change. You guys hear a lot about climate change causing like ocean levels to rise and global change and weather patterns and things like that. The other thing that happens is ocean acidification, which we don't talk about as much. So with ocean acidification now, we thought it is so great. We have the ocean and it's becoming a carbon sink, and it's going to absorb this carbon dioxide that we're putting into the air, and that's going to slow climate change, which it does, and that's good. But on the downside is now the oceans are getting too acidic. And we thought initially it's not going to be that bad. It's going to be okay because we're going to be able to replenish the carbonate in our buffer because of the weathering of the rocks. So the rock weathering is what's helping restore the carbonate to it and dying things, degrading, as well as restoring that carbonate. So we thought it's going to be fine. The weathering of the rocks is going, and the weathering of that limestone is going to restore our carbonate amount, and it didn't, and we're running out, and by running out now it's shifting our pH. So that's how it relates into the carbon cycle. So you should be talking about that as part of your essay. What questions do you have post that?
But I was going to say before, peat from a fossil, so it's subject of carbon emission.
Yeah, Hannah.
So why are we running out of this? Because the ocean's trying to get the...
Yeah, so that's a very good question because that now shows me to the next bit. So if you guys remember, this is a reversible equation and it's going to try to move in the direction to fix the disruption. And so the main disruption that we're having with ocean acidification is that we're having a lot of the hydrogen ions. Since we're having so many hydrogen ions, it's forcing the reaction to go this way, using up the carbonate. And like I said, we aren't weathering rocks fast enough to replenish that carbonate, because remember, it is the carbon cycle. The other thing that's also a big problem is that this carbonate, living things depend on it, such as like shelled organism, corals, that sort of thing. And so if that carbonate is not available for them, they then can't build their shells because it's now being used to neutralize the acid in the ocean. The other thing is because we've diminished our carbonate supply so much, it's now even starting to dissolve the shells of organisms as well. So it's real bad.
So it's because we keep putting stuff on that side?
It's because we keep putting in that carbon dioxide, it's getting dissolved, it's forming those hydrogen ions, and then it's trying to neutralize it.
Yeah.
And so remember how I said at the beginning with buffers, where's my buffer sheet? Buffers aren't magical things that work forever, they have a capacity.
Yeah.
When we hit the capacity of that buffer, it then changes pH. And so we are starting to hit the capacity, is what's happening. The other thing to keep in mind is, like I said, with the climate change and the warming of the planet, we're starting to melt the ice caps, and we are also diluting our buffer. And that's weakening its capacity as well. So it's a compounding issue. Yeah? Problems. Scary problems. All right. Keep going. One last thing, and then I'll show you guys a video. All right. I really like this diagram because remember how there's multiple steps in that equilibrium equation? There's the carbon dioxide, there's the bicarbonate, and then there's the carbonate. So because there's so many different components to it, and it's really affected by pH because that buffer is trying to release hydrogen ions, accept hydrogen ions to maintain it, at different pHs, you'll have different concentrations of the different components. So you'll have the carbonate, the bicarbonate, and the carbon dioxide. So our ocean is normally around 8, and from 8, this is what our ratios look like for carbonate, bicarbonate, and then carbon dioxide. So we actually have quite a high amount of the carbonate, which is good at that level, so that way organisms can use them in their shells and things. However, with the acidification process, we are shifting the pH down, and that's disrupting that equilibrium. And so now our ratios have changed. So as we start going to, say, for example, 7 pH, we're losing the carbonate ions. We're gaining more of these these hydroxide ions are pretty high regardless. But are getting rid of the carbon dioxide. So does that make sense? So that's what we're seeing with that shifting effect. So that's where the carbonate's going. All right? Questions so far? Carbonic acid is what's being formed when you dissolve the carbon dioxide into the water. And you have to remember it's a weak acid, so it's a reversible reaction. And you remember on that scale that I showed you guys yesterday, it was the weakest of the acids that were on that poster. It doesn't fully dissociate. But it's dissociating enough that's causing a problem. All right, cool. I'll pause the recording here, and I'll show you guys a video on ocean acidification, and then I'll go back and give you some more notes. Sorry, like I said, it's going to be a little bit note-heavy this lesson. All right, so what I'm going to do is I'm just going to first pour some water into a beaker. And this is obviously the uncarbonated water. And I'm just going to add some indicators so that way we know what water is without the carbonation process. So that's just normal water. And I put universal indicator, and we see how it's green. So that tells me that that water is neutral, which makes sense. That's what we want. Now what I'm going to do is I'm just going to put that water into my soda stream bottle. We're going to measure the temperature of it. I did this last night, just tinker with it. It did kind of work, but it only changed it a few degrees. So, but it's a very minor change when it comes to this. It's not a whole lot. Where did I put the thermometer? And then we're going to carbonate it with my soda stream apparatus over there. And I made sure I got cold water because I'm hoping it'll make a more noticeable change than just the room temperature water. So it's starting to lower. Just letting it go. Put it on the docking camera if you guys want to see it. So all I'm trying to do is just put it in there with a thermometer and have a little read of it. Let's see, are you done moving yet? I think so. All right, so that's 5, 6, about 6.5 maybe, is the temperature of the water right now before the carbonation process. All right, so I'm gonna hook it up to my soda stream. So the soda stream is basically acting like our atmosphere, and it's increasing the amount of my carbon dioxide, and I'm forcing that carbon dioxide in. So we need quite a bit of pressure to carbonate water. So I've now carbonated that water. You can see that it's bubbly. Yeah, that's the whole point of carbonation. So basically it's thinking about what we're doing in the ocean. We're adding that carbon dioxide into the ocean. All right, let me quickly measure the temperature. See how that's changed. And then we'll pour some of it out into a beaker, and we'll see what that color looks like. I'll put the universal indicator in there to start with. Actually, no, we'll pour. I've already checked out the first one. All right, so let's see. So this one's temperature is now 5, 6, 7, 8 degrees. So it's changed from 6.5 to 8 or to about 8. So it's only increased about 1.5 degrees Celsius. But that's just from adding carbon dioxide to it. So I think that's pretty interesting to see. So if we're thinking about the dissolving of carbon dioxide gas into water, is that an endothermic or exothermic reaction? Exothermic, because the temperature is increased, so it's released heat energy. So the forward reaction is exothermic, and I'll write some notes on that. All right, here's my beaker. I'm pouring my carbonated water in there, nice and bubbly. And then I'm going to add some universal indicator to it to see if the water has changed. Someone mentioned that it looked like Fanta. It's not Fanta. So we see here, all I did was carbonate it, and we see such a dramatic change in that color. It's gone from that green color to now this orangey color. And when you drink soda water, you'll notice that's a little bit like acidic. Some people really don't like the taste of soda water. I like it. Yeah, because I like the carbonation. And you know how they say like, oh, soda water is a better alternative than drinking sugary soda drinks because you don't have that sugar in there, which is true. But it's not as much better as you think it is because there is obviously that carbonic acid in there, and that acid in the soda water is actually degrading your teeth. So dentists don't recommend it. They say just drink plain water. But I'm a bubble addict. I love bubbles. So anyway, that's what you see. So if you're ever wondering, it is definitely acidic. Are we okay with that so far? Yeah, pretty cool. It makes you rethink what you're doing. I'm still gonna drink soda water because I really like it. Okay, let's go back to the notes. So this is the last bit of notes, and then you guys are good to go. All right. Cool. So the other thing I wanted to then add, just gotta find. Oh. Oh, that's what I want. All right. So let me refocus that for you. So with the soda stream and with ocean acidification, you have carbon dioxide in the gas form and then carbon dioxide in the aqueous form. So that's when it's dissolved into the water. Obviously, it's a reversible reaction because I've put the carbonation in there. I could leave the lid of the container off, and then the carbon dioxide will start escaping. That's going to make my drink go flat. And so you can obviously reverse that reaction. Now, like I said, when we were looking at this reaction, we started at 6.5 degrees Celsius, and then after we carbonated it, it went up to 8 degrees Celsius, so that did increase. And so since there was an increase in that temperature, what that tells me is the carbonation process is exothermic. So I release heat energy when I'm dissolving that carbon dioxide. Now remember, when we're talking about endothermic and exothermic reactions, they always happen in a pair. So if the forward is exothermic, the reverse is endothermic. So we talked about how climate change is causing the ice caps to melt and increase the dilution of the ocean. What else is climate change doing? With big picture. It's hotter, it's the temperature. So with the increase in global temperatures, the good news is that it actually decreases the ocean acidification process. Because if I'm increasing the temperature of the Earth, I'm actually promoting more of that carbon dioxide to be released from the ocean. So that's the good news. It's sort of good news. So increase global temp. We promote the endothermic reaction because we're trying to use up that heat. So the good news is that there's less carbon dioxide being dissolved into the water and more carbon dioxide being released. I don't know if that's necessarily a good thing. Back into the atmosphere, which then continues to make it hotter. Blake's got the point. It's a positive feedback loop.
It's not positive, it's negative.
No, because if I increase the global temperatures, if I'm releasing more carbon dioxide, I'm increasing the global temperature. And then by the increase of the global temperature, I'm going to release more carbon dioxide. Yeah. So it's a positive feedback loop.
Yeah.
Yeah.
I'm thinking you're saying positive as in like positive as an emotional concept.
No, I'm talking about positive as in like, you know how there's positive and negative feedback loops? So like positive feedback loops, the whatever happens at the end point of that loop creates the first one to go forward again. So it keeps accelerating like a snowball, getting bigger and bigger and bigger. Whereas a negative feedback loop, the end point turns off the loop. So this is a creates.
So that's what they're talking about when they say there's like a
So it's just getting worse and worse. It's just
Yeah, we're very close to that point.
Isn't that fun? All right. Are we okay with all of that? Does that make sense? All right. Can I move it? All right. I'll stop the recording. I'll go back to the PowerPoint because there's a few more things I want to point out.